Okay, so we are going to talk in this video about the wave motion on an interval. So we are going to talk about the motion of the wave when we are having some interval that is going to be describing the wave that we are dealing with. And when we are dealing with something like this, we need to have some like initial conditions. Like we want to know what is the special case for the where that the initial condition is having velocity, or initial velocity, for example, is going to be 0, or initial displacement is going to be 0. Okay, so we are going to start with special cases first so that we can understand how it works. Okay, let's start with the case where that we have zero initial velocity. So there is no velocity for the wave, just it is going to be displaced from a certain position and leave it. Okay, so like if we have a string, for example, then we are going to like move it here, for example, and then leave it. So this, it would like making or giving to us some shape for this wave with different t's, and so on. Okay, so we are going to talk about the zero initial velocity in the beginning. Okay, now we will solve initial boundary value problem because we have used it many times before. Okay, the initial boundary value problems. I have already some videos regarding initial boundary value problems. Okay, you can check it on the previous video or in the in the YouTube channel. For the wave equation on a closed interval, we are having a closed interval from 0 to L. As we said, we are talking about some specific interval, okay, from 0 to L. Starting with special cases first. So we're going to make it easy for us. We're going to start with initial cases, special cases. We can solve and building toward more complex wave motion. So if we could understand like zero initial velocity condition and zero initial displacement condition, then we can build upon them and we can describe more complex wave motion. An elastic string of length L with fixed ends is released from wrist, take care, from wrist, which is zero initial velocity, from an initial position given. So we are going to, as I said, from initial position that we are going to give it, or we know it. Okay, as I said, as you have a string, for example, and then you are going to like hook it, pick it up here. You are moving it up, for example, here. So this is initial position here. Okay, with zero initial velocity, just you are putting it in this position and keep it and leave it after that. Okay. Now let's start with this. Let's assume that we have a function which is f of x equals to x f x between 0 and L over 2 and equals to L minus x f x between L over 2 and L. This is actually the case where that the string is being picked up at its midpoint. Okay, this is the case, like as I said before here, that we have an interval from 0 here to L. This is the distance L here, and from 0 to L over 2 we have x, something like this, for example, and whenever that we are in this part from L over 2 to L, it is going to be L minus x. So we have like two intervals inside our closed interval, okay, one of x and one of L minus x. Okay, so what we want from this, we want to describe this function as function of what? Remember, this is function f of x, right? It's only position. But remember that our wave equation, we are assuming this, it is going to be like wave. When we leave it, we are going to find that there is something going to happen and change with time. So we want to describe y of x and t of this equation, okay? Of this equation, or this function, of this function. So it is, we want to know what is the y, which is the position of any point x at any point time t. This is what we want to do. So we are going to use our skills that we have already trained before using our superposition that we have done before and using the Fourier series and so on, we are going to find at the end that if we use an infinite superposition, we are going to end up with y of x and t equals to the summation of these terms from n equal to 1 to infinity. It is infinite superposition of what? A coefficient Cn multiplied by two sinusoidals, sine n pi x over L times cosine n pi ct over L. So we have here x and we have here t, okay? And we have here also c. As I said, c, this is a constant. This constant, it depends on the robe itself, okay? Like the rho of the material of the robe, for example, the density of it, something like this. So this c, it is a constant that is representing the robe and boundary conditions, for example, or the density or the condition of the robe itself in terms of density and something like this. So it is known for us. So now we can distinguish that our wave equation is going to be function in x and t, but we realize that it is going to be like as if that it is a superposition of different, let's clean here, superposition of many terms, Cn, which is a constant, we do not know what is Cn exactly, times sine function times cosine function. The first sine function is in x, the second cosine function is in t. So we have x here, we have t here, but we do not know what is Cn this. Okay, we're going to use Fourier sine expansion, okay, and then we're going to end up with this nice equation that we already have explained something like this, similar to this before. We said that Cn is going to equal to, after some derivation, as I said, 2 over L from 0 to L. It is integration of the function fz sine n pi z over L dz, okay, where z, this is the independent variable, is going to be taken from 0 to L. Okay, so this is like z, it is related to Cn. So we have x, we have t, and we have here, yes, this z, okay, this z, which is going to be like related to Cn. Again, I want to like make it clear for you. We have a function, and this function we are going to represent it by a wave function, because we want to know what is the position of this string at different times. So we used our skills in Fourier expansion in general, whether sine or using infinite terms using Fourier series, and then we ended up with having Cn times sine something times cosine something, and we are going to represent this by this, which is the solution of the problem with zero initial velocity and initial position given by the function f. It is going to be like this. This is, if you remember, this is Cn here. Remember the function y that is going to be represented, which is the wave. This is exactly the wave, okay, function that we are dealing with. Again, in two terms, x and t, and you understood now what is the meaning of x and t, equals to 2 over L summation of many terms. We have summation. Why it is summation? Because remember that if we started with picking it up something like this and leave it, we're going to find that it will be something like this, and then something like this, and then like this. So there is what we need, a function that is going to represent these positions, these shapes, in a very accurate way. And as we have discussed before in Fourier series and Fourier sine and cosine expansions, they are perfect ways and methods in order to represent any kind of function that we have, right? Do you remember that any kind of function that we have, it is going to be represented easily by Fourier series, for example, or sine and cosine functions. So we are dealing with this. This is why we need these many terms here are going to use. And we are going to make it easy by saying that we have Cn, a coefficient that is going to be function of f of z times sine n pi z over L of the function, where z is our independent variable that is going to be limited from 0 to L, and we are talking about an integration here, times sine n pi x over L cosine n pi c t over L. As I said, this term representing the x parameter or x variable, this term is representing the time variable, okay? And this is going to be a coefficient. This is going to be a coefficient. You're going to find that it's like a constant at the end, okay? So that it is going to give us the description. After taking many terms of these, we're going to end up with the real description of the wave at any particular time for any particular c, for example, c equal to 2 or 1 or anything, which is this constant. Okay? Okay, so this is what we can understand from the wave function based on zero initial velocity. I want you to remember this equation. It's very simple and easy to remember if you could give it these three terms as I have mentioned to you. Okay, we are ready now for an example, and I think that in the next video I'm going to talk about an example. Thank you, and see you in the next video.